Okay, this will be the lecture for chapter 27. We're going to be talking about light. More specifically, we're going to be talking about color. So I'll talk about how color is actually more physiological, and I want to talk about the physics of it, and I'll talk about how we can see light that has been reflected, we can see light that has been transmitted, and how do we go ahead and mix the various colors of light. And I'll talk about the primary colors and the secondary colors. And then I'll kind of change gears and I'll talk about, age-old questions, the why. Why is the sky blue? Why are sunsets red? Why are clouds white? And why is water greenish blue? And why is water in, like, the Rockies a really pretty greenish color? So, first of all, let's talk a little bit about color. Color is kind of physiological, and it's in the eye of the beholder. And it also kind of depends on what type of light that you're being illuminated with. For example, we have this lady right here. She's putting on some lipstick with this incandescent light bulb, and she sees kind of a pinkish color. And then she goes outside in the sunlight, and she sees a bright red color. And what's kind of going on is being illuminated by different color of light, and so we're perceiving something that is slightly different. So we do have to bear in mind that when we talk about color, we're talking about something that is slightly subjective. And we all probably know that women are much better than men at picking out colors. And here we have the names of the colors, according to women, and here we have the names of the colors according to men. And this is kind of amusing, but it's also kind of true. Now, I want to kind of, bear in mind that color is subjective, and what I perceive as orange might not be quite what you perceive as orange. So there's kind of a smear when we talk about colors, like a smear in frequency. In the physics sense, I do want to talk about colors, and more specifically, I want to talk about wavelength, or the frequency of light. And this comes back to what light is. At the end of the day, light is going to be an electromagnetic wave, wiggling electrons, if you will. And what we can do is we can talk about frequency, and we know that frequency is going to go up as we work our way up this chart right over here. And we can talk about things, or pieces of light that we can't see. AM radio, FM radio, microwaves. We can talk about infrared light, can't see that. We can talk about this little teeny tiny sliver of light that we can see, and we're going to call that the visible portion of the spectrum. We have our UV, we have X-rays, and gamma rays. Now, here I have it in the language of nanometers. Remember, nano is times 10 to the negative 9th meters. And we can pretty much see from roughly 400 nanometers up to about 700 nanometers or so. And what we have is we have our standard Roy G. Biv, so our red, orange, yellow, green, blue, indigo, and violet. Again, we still have frequency increasing in that direction right over there, and that's decreasing in the language of wavelength. So what we can say is color is going to depend on the frequency of light, and we could also say wavelength, as long as we bear in mind that we're talking about light in a vacuum, where the speed of light would be equal to wavelength multiplied by the frequency. Wavelength is slightly not the best way to talk about it, because if we were to talk about light in material, it's going to slow down, so this is no longer c. The frequency would actually remain the same, and the wavelength would go down as the speed slowed down. So wavelength is not as appropriate as frequency when we talk about the color of light, but it's good enough. The lowest frequency that we can see is red, and then we have their Roy G. Biv. I'm not going to go through that again. And the highest frequency would be violet. Below red we have infrared, and above violet we're going to have ultraviolet or UV. Now, not all light is created equally, and our eyes are actually not going to be equally sensitive to all colors of light. Our eye actually is going to have some sensitivity primarily in the green, and it's going to peak around 550 nanometers. Probably not surprisingly, this is actually going to be green light, or yellowish greenish light, and that's actually where the sun is also going to peak in what it puts out at. So it kind of says, we kind of evolved such that our eyes are most sensitive to the sun. We're not very sensitive to the reds. This is why, like in astronomy telescopes and stuff like that, they have the red lights, and that's because, well, our eyes aren't going to get blinded by it, if you will. We're also not quite as sensitive to, the violets and stuff like that. bear in mind that when we see light, what we're actually going to see is we're going to see a mixture of all the colors of light that are incident upon it. And it does kind of depend on perception. A couple of years back, there was this dress that went viral, and the question was it blue or black, or was it white and gold? And people said different things. Now, with the resolution of my screen in this particular image, I personally see this as kind of a brownish and a bluish, but I'll leave this up to you all what you all actually see. So, ask yourself the question, which of these can the human eye not see? Well, we actually can't see infrared, we can't see ultraviolet, we can get sunburned by it, but we can't see it, so this one's actually going to be C, both A and B. So let's talk about what we see when we see light, and before I talk about that, I actually want to talk about what white light is and what black light is. White light is actually going to be all the colors of the rainbow. And so we could actually say that would be red plus orange plus yellow plus green plus blue plus indigo and plus violet. So it's going to be all the colors of the rainbow mixed together. In a couple of slides I'll say we only need 3 of these. These are the primary colors, but for right now we're just going to say white light is a mixture of all the colors. If I were to talk about black light, well, black is actually going to be the absence of light, and so there's going to be no colors of the rainbow that we're going to see. So black light would actually be no light. And I probably shouldn't say black light, but I'll just say white is all the colors, black is no colors. What's going to happen when we see something? Well, suppose I had some white light coming off of this sheet right here, and I had a pink rose in my hand. Well, what I'm going to see is I'm going to see the color that is reflected back to me from this rose, and since white light is going to be all the colors, what's reflected is just going to be the red. All the other colors, well, they had to go somewhere. They were probably absorbed by the rose, so it's selectively going to reflect only certain colors or certain wavelengths. Now, suppose I had a red ball and I were to shine some white light on this red ball. Well, remember, white light is all the colors of the rainbow, and this ball is going to selectively reflect just the red. It's going to absorb all the other colors. So the rose is going to absorb most of the light, just reflect the red. The same is true for that ball. If I were to shine some red light on this ball, and just red light, no other colors, then obviously the ball is going to appear to be red because, well, red light definitely has red in it. But suppose I were to go ahead and shine some green light on this ball. So here's my green light shining on this ball, and I don't know about you, but this ball is going to look black. The reason for that is because green light actually doesn't have any red in it. So there's no red reflect back, therefore this thing is going to look like it's black. The key thing to kind of keep in mind is objects only reflect the frequencies that are present in the illuminating light. If there aren't the correct frequencies, then it's just going to look black. Now, let's just really quickly talk about transmission. I will come back to reflection in a little bit. The color of a transparent object is going to depend on what colors it lets go through it. So suppose I had my white light and I shine that thing onto some glass, and the glass only lit blue through it, then what I'm going to see over here is I'm going to see just blue light with my eyes. Now, light is essentially carrying some energy from one object to the other, and while this glass is blue, what happens to all the other colors? What happens to the red? What happens to the orange, the yellow, the greens, and the violets? Well, they're going to get absorbed by the glass, and where does the energy go? Well, the energy is actually going to go into warming the glass up, so the energy just doesn't go away. So now really quickly, let's talk about what happens if we were to mix some colored light, and I've kind of already gotten a little bit ahead of myself and talked to this. Suppose we had an object, and this object might be something like the sun. The sun is actually going to be putting off all the colors of the rainbow, and if I were to look at the brightness of the colors versus the frequency for what the sun puts off, it turns out that it's not going to put off all colors equally. It's going to have some frequency distribution that is slightly uneven, and as I alluded to earlier, the sun is going to peak in brightness in the green portion of the spectrum, so around 550 nanometers. the sun's going to put off less red, and actually it's going to put even off less violet than it does any of the other frequencies. This is kind of related to why the sky is blue and why the sky is not violet. It turns out that it doesn't put off enough violet for us to be able to see it. But just kind of bear in mind the sun puts off all the colors of the rainbow, and if we were to take these guys and mix them together, then white is essentially going to be equal to all of the frequencies added together. Now, it does turn out that we can not just talk about the Roy G. Biv, if you will, but we can actually break these into three categories. We can break these things into the reds, we can break them into the greens, and we can break these guys into the blues, and we can make any other colors with these three colors, and these are actually going to be what we call the primary colors. And if you were alive like 20 years ago, then we actually had these things called RGB monitors, and they were red, green, blue monitors, and they were absolutely horrible compared to like the 4K televisions that we have today. And they had three colors, and they used them to attempt to mix together all of the colors. So again, these are kind of the primary colors. We can add them together to make any other color in the spectrum just by mixing together certain amounts of each one. What we can do is we would have our reds, we can have our greens, and we might have our blues, and we can shine these guys together. So here's my red, there's my green, and there's my blue, and you can see we're producing some other colors. And I want to talk about these other colors. I do want to say that right here in the middle we're going to have our white, and our white is going to be red plus blue plus green, adding all those three primary colors together. Now, not to belabor the point, but it is kind of important, but white light is going to be the combination of many wavelengths, or we could even say that it's roughly going to be equal amounts of red plus blue plus green. However, if we were to mess around with the relative amounts of these, then we could produce other colors. And for example, we could have a red hot poker, and that may have some blue and some green in there, but it's going to have much more red than, say, blue light, or much more red than green light. And at the end of the day, red plus blue plus green is going to be the white light. So picture blue plus green plus red. You add all these guys together, and we're going to get some white light. Now, this is kind of another picture here where I've taken the three screens, or the three projectors that we were looking at, and we're going to have our reds, and we're going to have our greens, and we're going to have our blues. And the question is what colors do we see when we mix these guys together? And I don't know about you all, but where these two overlap, we're adding them together, and we're going to get yellow. Where these two overlap, we're going to get magenta. And where these two overlap, then we're going to get cyan. So let's kind of go over here and take a look at this. Red plus green. Well, here's my red, here's my green. We're going to get yellow. Red plus blue, we're going to get magenta. And green plus blue, we're going to get cyan. So we can talk about these as our three primary colors, and we can mix them together in relative amounts to get any color that we want. We could also think of this kind of like subtraction. For example, if we were to talk about magenta, well, here we have, actually, I'll go ahead and get rid of this. Here we have our magenta. And what is magenta? Well, magenta is actually going to be where there's no green. See, all the green is over here. Right here, we don't have any green. So we could think of this as a subtractive color as well. Green is going to be, or the absence of green would be magenta. If we were to talk about cyan for a little bit, here we have cyan. We don't have any red in cyan. So the absence of red would be cyan. And you can make a similar argument for yellow not having any blue in it.